Case study: Advancing Cyber Defense, Navigating Multidimensional Challenges of Reinforcement Learning at CyberShield Inc. In the control room of a leading cybersecurity firm, CyberShield Inc., the atmosphere was tense. The team was in the midst of deploying a new reinforcement learning-based defense system designed to protect against ever-evolving cyber threats. The star of the show was Alex, a senior machine learning engineer, tasked with fine-tuning the RL algorithms to cope with the complex dynamic nature of cyber threats. The first challenge Alex faced was the non-stationarity of the cyber environment. Unlike a game with static rules, the cyber landscape is dynamic and adversarial. CyberShield's network was continuously under threat from attackers who adapted their tactics, challenging the RL system's assumption that the environment's dynamics remain consistent over time. How can the RL system be designed to adapt to these changing conditions without frequent manual interventions? To tackle this, Alex implemented a continuous learning framework. The RL algorithm was enhanced to constantly update its policies based on real-time data, enabling it to adapt to new threats as they emerged. This approach, however, introduced a significant computational burden. The system needed to process vast amounts of data and update its learning models continuously, raising concerns about its stability and reliability. Another critical issue was the exploration-exploitation dilemma. Effective cyber defense requires finding a balance between trying new defense strategies and leveraging known, effective ones. For instance, an RL agent could explore unconventional firewall configurations, but this could inadvertently create vulnerabilities. How should the team balance the need for exploration with the imperative to maintain robust security? Alex addressed this by implementing a conservative exploration strategy. Techniques like epsilon greedy policies were used with a low epsilon value, meaning the RL agent would primarily exploit known strategies while still occasionally exploring new ones. Additionally, safety nets were introduced to monitor and revert potentially risky configurations, minimizing the chances of creating exploitable security gaps. The curse of dimensionality posed another formidable challenge. The high-dimensional nature of CyberShield's network environment, characterized by numerous configuration settings and potential actions, made it impractical to use traditional RL methods. How could the team manage the computational complexity and ensure efficient learning? Deep reinforcement learning was adopted to approximate value functions or policies using neural networks. However, this introduced its own set of challenges, including stability issues and the need for extensive training data. To mitigate these challenges, Alex employed techniques like experience replay, which involved storing and reusing past experiences to stabilize learning, and prioritized replay, which focused on more informative experiences to enhance learning efficiency. Temporal credit assignment was another hurdle. In cyber defense, the impact of an action, such as deploying a security patch, might not be evident until much later. How can RL algorithms effectively handle such delayed rewards? To address this, Alex integrated eligibility traces into the RL framework. Eligibility traces allowed the system to maintain a record of past actions and states, creating a bridge between immediate actions and delayed rewards. Hierarchical RL was also explored, breaking down the overall task into subtasks with shorter temporal spans, making the learning process more manageable and effective. Adversarial learning brought its own set of challenges. In cybersecurity, adversaries are intelligent agents constantly trying to deceive the defense system. How can the RL-based system be designed to anticipate and counteract such adversarial behavior? Alex incorporated game-theoretic principles into the RL algorithms. By modeling the interaction between the defender and the attacker as a game, strategies could be formulated to consider the adversary's potential moves. Additionally, adversarial training was conducted, where the RL agent was trained against simulated adversarial attacks to improve its robustness. Sample efficiency was a pressing concern. RL algorithms typically require large amounts of interaction data to learn effective policies. In a high-stakes environment like cybersecurity, generating such data can be impractical. What methods could be employed to improve sample efficiency? Transfer learning and few-shot learning techniques were explored. Transfer learning involved leveraging knowledge from related domains or previous experiences to accelerate learning in the current domain. Few-shot learning aimed to develop effective policies from minimal data, proving invaluable in scenarios where data was scarce or costly to obtain. Lastly, ethical considerations could not be ignored. Autonomous RL agents in cybersecurity raise questions about accountability and bias. How can the team ensure that the RL system operates ethically and does not inadvertently introduce biases or prioritize certain assets over others? Alex and the team took a multidisciplinary approach, integrating insights from computer science, ethics, and law. They established guidelines for the responsible use of RL, ensuring transparency in decision-making processes and implementing mechanisms for human oversight. This approach helped in addressing potential biases and ensuring accountability in the event of a system failure. In conclusion, Alex and the team at CyberShield Inc. navigated the multifaceted challenges of applying RL in cybersecurity. By continuously adapting the RL algorithms to the non-stationary environment, balancing exploration and exploitation, managing the curse of dimensionality, addressing temporal credit assignment, incorporating adversarial learning, improving sample efficiency, and considering ethical implications, they developed a robust and adaptable cyber defense system. This case study underscores the importance of interdisciplinary approaches and continuous innovation in overcoming the theoretical challenges of RL applications in cybersecurity.